You need three things to get a storm. You need moisture, which would be obvious, instability, which you can get from having cool air coming in aloft, or else heating up the ground as well, and you need lift. You need lift from either aloft or else from the surface, like a surface front, or a combination of both. Once you get a storm, really there's only three types to think about. Pop-up pulse type, like summer garden variety, that don't last long because there's no shear aloft, so they just go up and collapse. There's linear complexes, like a line or a bow echo. And then there's supercells, just a single rotating updraft produce the tornadoes and majority of the severe weather. Moisture for our severe storms is going to come from the Gulf of Mexico. It gets heated up, transported northward on low-level winds. Like this day is April 14th, 2012, a big outbreak in Kansas and Oklahoma. And this is about 6,000 feet off the ground. The green lines are higher dew points, so all the moisture you can see is in this stretch here. While a lot of the Gulf's dry, all the moisture just ended up over here and is returning north ahead of a big trough. Upper level lows out west coming in. So the moisture for this day is just affecting northward on the low level winds. So on this particular outbreak day, you had those low level winds bringing in the warm moist air off the Gulf. You have this big upper trough or storm system out here in the west moving east. Big cold pocket essentially. So as that moves east, it brings in colder air aloft over the warming low levels. So they're warming and it's getting colder aloft. So you're building the instability part. You're also going to add the wind shear with the winds with the storm system. And also with this upper jet, this is up about 30,000 feet. You get divergence where the winds spread apart aloft and that draws that air upwards from below. So there's one source of lift coming in with this trough. And you'll have a dry line in Kansas going down through Oklahoma, and a warm front was up here this day along the Nebraska-Kansas border. So those surface boundaries are also part of the lift. They push east and just otherwise converge air at the ground that forces it upwards, and it gets help aloft by this upper jet. Here's a surface map for that same day, April 14th. See all the winds are off the Gulf down the ground, transporting rich air northward. Surface low here. Remember that big upper trough's coming in, providing wind shear aloft and cooling air aloft. You look for the front by these different wind directions. Like here it's out of the southwest. These are all out of the southeast. There's a surface low here, so the dry line extends south. See the dew point's 24 compared to 62 there. And up here, the warm front will be, you can see it goes southeast and they turn towards the easterly. Here's a northeast, east. Temperature 72, 71. Temperature up here is 62 though. That warm front's here and lifting. So you have storms that'll fire along the warm front from the convergence, the lift that's providing, also along the dry line. Again, the red, the top number on these reports, the obs are temperature, and the bottom numbers, dew point, 72 degree temperature, 63 degree dew point in Dodge City. Pretty high for mid-April, that far west. As a reference, you can see here the storm reports from that day. Big tornado outbreak in Kansas and northern Oklahoma. See the warm front, got a few of them. Didn't go much further south than there. Really, the dry line just went nuts, Kansas and Oklahoma. So to get a storm, we need moisture, instability, and lift. To get a supercell, or even just a more severe storm, you need wind shear aloft. Now, this is a 300 millibar map, which is roughly 30,000 feet up. You see where it bulges north like this, there's a ridge. There's sinking air underneath the ridge and lighter winds aloft. The trough up here, where anywhere where it dips south, you have a trough. The jet dives north, bulges, you have a ridge. But anyway, to get a supercell, you need wind shear aloft. Say your storm fired right here on the Kansas-Nebraska border with light winds aloft. You have a storm that goes up there, and if there's no winds aloft, the the precip that's happening away from the updraft, it simply has to fall back down through it, killing the updraft. So to get a supercell and more severe storms, you want wind shear aloft. This air will rise and get vented as it cools into precip. That precip will fall away from the base down here, allowing more warm air to keep rising. Keeps going and keeps going. Before continuing, it's worth understanding a couple things. First is Zulu or UTC time. It's just a way that is universal to give time, and it's what the various weather things come in. Basically, after spring, for the central time zone anyway, you subtract 5 to get the time. So if it's 20Z or 20 UTC minus 5, that'd be 15 military time, which is of course 3 p.m. Say it's 12Z, you subtract 5, you get 7, so it's 7 a.m. 0Z would be the same as 24, so 24 minus 5 is 19 military time. 19 military time, 7. So basically, when you see the times on charts, plots, and whatnot in Zulu or UTC, you got to subtract 5 for the central time zone in the spring. In the winter, after the time changes, you subtract 6 then. But for most of the spring season, it's subtract 5 to figure out the time. To understand much of this forecasting stuff, you're going to need to know the relative heights given in the millibars, because everything's coming in millibars on all these the models and whatnot we're going to look at here. But 300 millibars is roughly 30,000 feet. 500 millibars is roughly 18,000. 700 millibars roughly 10,000. 850 millibars roughly 6,000. And you pretty much you can get by with just knowing, those 4 right there. That covers a lot of the storm. Anyway, you need to grasp that. It's worth giving some context to things now with one supercell example. This one from July 13th, 2009. The storm could be upwards of 60,000 feet or more, but most are usually, 40 to 50,000 or 50,000 plus for the tops. And now you can look at these heights in here. You go back to remember those millibars. 6,000 feet is roughly low-level jet height, or 850 millibar. 18,000 feet was the 500 millibar. That's kind of your mid-level steering winds. 30,000 feet, 300 millibar was up higher, closer to the anvil. So this storm was probably 50,000 feet. So you think about that, that's almost 10 miles tall, and then it's leaning over as well. So as that moisture vents, it's venting a long ways away from where the base is, or at least a lot of it is. That's good. This is looking to the northwest, so you got these southeast surface winds going into it, and you also had southeast winds and 6,000 feet. Pretty much that whole depth is your moisture and instability feeding into the storm. And cooler, dry air comes in aloft. Dry air is heavier than moist air. It's also colder up there, so just all adds to instability. And hopefully you have a jet aloft helping with lift. As long as you keep venting that precip away from the updraft, which is pretty much right here from this edge to this edge. One rotating updraft goes way up and leans. This whole anvil's spreading out from this one updraft. And it's moving towards the southeast. So if you imagine it going up and tilting with the west winds aloft and moving this way, just dumping lots of precip out this way, far from the base. Here's an example of the radar at the time. I'm about where the X is. In the circle you see on radar where the hook echo is, that's basically right where your storm is. The updraft is all right here, and this is all vented precip from the winds aloft as it tracks this way to the southeast, and the winds are from the west aloft, moving into the inflow too. So you got that inflow going this way into that updraft. Again, is right around this circle area. There's one more image example to convey the size and where things are blowing. Same storm moving southeast, west winds aloft, venting this way or south. Rough size of the updraft, the actual storm updraft is right in here. goes up 50,000 feet, leaning over this way as it moves this way. The winds blow it precip even further out. To give you an idea how much distance we're talking, about 30 miles or more that this precip is being blown out from where the base of the storm is. Also on the scale note, this is the size of the anvil coming off this one supercell. You got one updraft about, somewhere in here where my hand is, and it's leaning. Your winds are 55 miles an hour from the west up here, and it's moving this way. So all this blow off here is from the one updraft. The updraft can be so strong that some of that blow off as it spreads out actually pushes up into those winds aloft. It's more bubbly on that side. Precip being spread clear out here on the radar. The rest of the clouds just really stream out for miles. This is a sounding from North Platte on that same day, July 13th, 2009. First off, you can see it says July 14th, 0Z. So if you subtract 5 from that, it's 7 p.m. on the 13th. This was the balloon that the Weather Service in North Platte they sent up. On the left, you can see the millibars, 700 millibars, 500, 300, 200. You can see the heights given near them. So again, 700 is roughly 10,000 feet. And you can see at the bottom, this is the temperature. So the red is the actual air temperature. Balloon goes up. This is what it's reading as the red line. But these are going this way. The temperature, like the 0 Celsius line, this dashed line going this way. So up in this area is where the actual air temperature is 0. Where down lower you can see it's closer to 20 C. You got to remember these lines for temperature are going this way. And the green line is the dew point of the air. See, only the lowest few thousand feet where that moisture is. Good depth of it. And this line is the virtual air temperature, which gets a little confusing, but basically if you fire a storm, you lift the air that predicts the temperature of that air as it rises. It's going to cool. Notice it's warmer than the actual air temperature. So all this area in here is your CAPE, or your convective available potential energy, your instability measured in this region here, which is huge on this day, 4,700 CAPE, all in here. You can see over here is the wind flow that it read as that balloon rose through the air. You can see down low it's southeast winds at 20 knots, quickly turning to west winds. Only 20 knots even up here near 500 millibar, 25 knots, 30 knots. But then up higher, you're talking 50 knots, 60, 65 knots out of the west. All that warm, all this low level warm juicy air is being blown into the storm from this way. And it's rising quickly. And then up here, pretty much where your anvil is going to be, where your rising air is going to be the same temperature as the actual air by this point, so it's not going to want to rise anymore. You can have some motion to this, so you can get an overshooting top on the storm that continues up through here, and then it cools off. So your anvil is kind of blowing out about this level. There'll be a lot more on these soundings. They're really useful, especially for the cap and the moisture depth and how the moisture depth looks. So anyway, again, it's just a balloon the Weather Service sends up and measures the actual air. Since everything's given in knots, I figured I'd show real quick how to convert that to miles per hour. Basically, they're really close. It's to get miles per hour, you times the knots by 1.15. The 25 knots is 29 miles per hour. 55 knots, 63 miles per hour. 100 knots, 115. Here's a sounding from Omaha, Nebraska on a big day in South Dakota, May 22nd, 2010. You can see again the red line is the temperature of the air as the balloon rose several thousand feet, 30, 40,000 feet plus. Down here near the ground, you can see temperature goes up. Again, these are the temperature lines. So if it's going from here and getting closer to that 20 there, it rose, then it falls again, then it rises a lot there, and then it falls again going up. You can also notice the dew point line right on top of that. You can assume there's clouds when it's that saturated to the temperature line. Anyway, this is a low level inversion. Happens at night. Lose the daytime heating, your ground cools, the low levels cool. So as you heat the day, you're going to erase that. But then there's a cap, a loft. This is just under 700 millibar where it just shoots up. Now look at this sounding later in the day after the sun got on things. I'll go back and forth. Watch the ground temp, the bottom of the line where it starts at the ground. You can see it warms up a lot by 7 p.m. But still there's a big jump here. There's a cap even in the evening. You see if you watch that cap layer, it even warms as the day goes on. It goes from over there to over here. So you erase that low level inversion with the heating, but you don't erase the cap aloft. And the cap's still fairly low, but that's the cap level there for this day. There was no lift or front near Omaha, so you weren't going to get a storm anyway, but that just shows the cap. So where does that cap come from? Well, it comes from the west. Terrain out here is higher up, and it warms. In these troughs that come in, the first thing they do is move that warm air east, and that warm air comes east off the ground, about that same height. So 10,000 feet or lower, somewhere around there, it comes out, and that warm air caps off the air below it because it's so much warmer. So that's the first thing the troughs tend to do, is bring the cap east. But after they keep moving, they start bringing in this colder air that's associated with the trough itself, and that will erase that cap. So that's your timing. It just depends on how that comes in. You can watch if I flick back and forth. You watch. It's hard to see these, but here's a 12 Celsius line. You can see when it moves east, it shoots it up. It kind of tries to move that cap up this way. See how that 12 just bulges up here? That whole cap, all this warm air right here, shoots up this way on these southwest winds. This is 700 millibar, by the way. Roughly 10,000 feet up where that cap is. Just noses that cap upward. You can get a few things on the cap deal from these two soundings on the same day. Both those, the May 22nd, 2010 tornado outbreak in northeast South Dakota. Here's Omaha sounding again, where it's very capped. See, whole going upwards, the air is cooling, but then it's warming, then it's cooling again. So this air's got a big area of hotter air above it. Not gonna let all this moisture go up. So you need to cool this off. You can only warm so much, so you really needed to cool this area down. But also that map I had before was 700 millibar, which is this level here, 10,000 feet or so. Remember that 12C line on there? That's what this is right here. Right about 12C. You follow these lines up where it crosses 700 there, it's about 12C, just like that map had. So according to this one, 12C is really bad, even though the cap's worse below that. So you can only tell so much by that alone. 12C is pretty warm. If you cool that off, this line would be over here somewhere. Or if you warm this all up, which is the case on this. Watch when I show Aberdeen's sounding. See, it's the same at 700 millibar pretty much, but there's no cap at Aberdeen. So seeing that 12C on that map really only told you so much. You really needed to look at the sounding to see how the air was below that. See, it's a lot cooler in here. If I switch again, and that's Omaha. Omaha with the strong cap. Aberdeen with no cap really. It's all cooling as it goes up. Meanwhile, really your 12C or your 700 millibar temp was the same, about 12C. It's a little cooler in Aberdeen, but not that much. So it really helps to use the soundings, the forecast soundings, to look at where that cap is and how bad it is. If you saw this on a forecast, you know there's not going to be any storms there. That cap's just really severe. And even that day, it looked pretty bad. Because you see that 12C bubble in some of the soundings. They don't look real uncapped. So it's just kind of like, I don't know. Pretend that cap level is up in here somewhere. You have a lot of warm air. A lot of days it'll try to go. Low levels will be convective, but the storms rise up and they hit the cap and they just kind of fall apart and turn to mush because they're hitting that warmer air and they just dying. They're not rising anymore. A lot of times the days start off like this when that cap's getting erased aloft by cold air coming in. Storms try and go, it's still too warm, still too warm. Finally, when enough cold air comes in, they bust through that cap and then they're allowed to continue punching way up and anvil out. That's how that works. Comes in and cools off. Some days it doesn't get cold enough aloft. Usually by this point in the late day, you're not going to get any more low-level heating to get up through that cap, erase it. Just need it to come in and cool down aloft. And some days you get a cap bust. Some days you're close. You're getting low-level cumulus clouds. Try and turn into big storms, but they just die out.